Okay, let's jump right in. We're doing a deep dive today into something called the cosmic shoreline. Sounds intriguing. It's about exoplanets, right? Specifically about their atmospheres. Or maybe
Yeah.
lack thereof.
Exactly. Think of this vast cosmic ocean filled with planets. Some have atmospheres, some are just bare rock. This idea, the cosmic shoreline, helps us understand the dividing line. Why do some keep their air and others lose it? It's shaping how we hunt for life out there.
Right, because finding an atmosphere is sort of step one for habitability, isn't it?
Pretty much. And what's interesting is, for a long time, the focus was mostly on how planets get their atmospheres, outgassing, delivery by comets. But
Yeah.
the cosmic shoreline concept, which Kevin Zonnel first really dug into, flips that. It asks, how do they lose them?
So it's about atmospheric loss.
Precisely. It's this metaphorical line. On one side, planets have enough gravity, a high enough escape velocity, and aren't getting totally blasted by their star, so they hold on to their gas.
And on the other side,
On the other side, either the gravity's too weak or the star's radiation is too intense and poof, the atmosphere gets stripped away over time. So it's like a map for astronomers. Helps us figure out, okay, which planets are the better bets for having air and maybe life.
that makes sense.
Right.
And I know a big part of this conversation involves M-dwarf stars, right? The most common ones.
Oh, definitely. M-dwarfs are, they present a real challenge. They're smaller, cooler, so planets need to orbit close to be warm enough for liquid water.
Into the traditional habitable zone.
Right. But the problem is, M-dwarfs, especially when they're young, but even later, can be incredibly active. They blast out huge amounts of X-rays and ultraviolet radiation.
The M-dwarf peril, as some call it.
That's the term. And that intense radiation over billions of years can just erode an atmosphere right off a nearby planet. It complicates that whole habitable zone idea significantly.
So the big question is, can planets around these stars actually keep their air, given how common these stars are?
That's the multi-billion-dollar question, really. And we're getting some crucial data now, especially from JWST.
Webb, what's it showing us?
Well, there's this fascinating case study. Gliese 486b. It's a super-Earth, bigger than our planet, orbiting an M-dwarf that's about 6.6 billion years old. So it's had a long time to potentially lose its atmosphere.
What did they find?
They measured its dayside temperature. Get this. It's a scorching 865 Kelvin.
Wow, that's over 1,000 degrees Fahrenheit.
Exactly, way hotter than Venus. And that extreme heat strongly suggests there's very little, or maybe even no, atmosphere there.
How does the temperature tell us that?
Because a thick atmosphere acts like a blanket. It would circulate the heat, moving it from the hot day side to the cooler night side. You wouldn't see such an extreme dayside temperature.
Okay, so the heat is just staying put on the side facing the star.
Pretty much. It implies there's nothing substantial there to spread it out, and findings like this are incredibly valuable. They help us actually plot where that cosmic shoreline lies, especially for these M-dwarf systems. It suggests maybe we need to look at more massive planets around M-dwarfs, ones with more gravity, or planets orbiting a bit further out, even if they're colder.
So Gliese 486b helps pin down that boundary.
No.
But you mentioned earlier the concept itself might be evolving. It's not just a sharp line.
That's right. It's looking less like a rigid fence and more like a fuzzier boundary.
Fuzzy how?
Well, newer models are starting to include other factors, like how much water and gas volatiles did the planet start with. A planet with a huge initial reservoir might hold on for longer, or even if stripped, maybe retain some deep inventory.
The starting conditions matter.
They matter a lot. And even more intriguingly, there's the idea that planets aren't necessarily lost causes forever. They might actually regain atmospheres over cosmic time.
Regain them.
Maybe through volcanic activity releasing gases trapped inside the planet. Or perhaps getting hit by lots of comets or asteroids later on, delivering fresh volatiles.
So a planet could cross the shoreline, become barren, but then maybe come back.
It's a possibility we're seriously considering now. This makes the whole picture much more dynamic, doesn't it? The search becomes even more complex, but also, I think, more exciting.
Absolutely. It's not just a one-way street to atmospheric loss.
Exactly. So ultimately, this whole cosmic shoreline concept, even as it gets refined, is a crucial tool. It helps us filter through the thousands of known exoplanets. It guides us on where to point our best instruments, like Webb, to look for those telltale signs of an atmosphere. And maybe, just maybe, biosignatures within it, signs of life.
It's about focusing the search where it's most promising.
Precisely. Understanding the basic conditions needed for an atmosphere to stick around.
So here's something for you, our listener, to think about.
M-dwarfs are the most common stars. If their planets have this tough time holding on to air, as Gliese 486b suggests. But then again, if the shoreline is fuzzy and atmospheres can potentially be regained, what does that really mean for how common or how resilient life might actually be out there in the universe? Makes you wonder, doesn't it?